brings us to statistical inference. So basically when we're inferring things. I mean, this is the whole point of gathering data, stats. So we can look at the data, make predictions about what's going to happen, infer things, and then make changes if we need to, that sort of stuff. It assumes that when we sample the data, then we can use it to make predictions about the larger population. Okay? We tend to sample rather than get every piece of data. Now, what is sampling? Well, that's when we just select particular things from the population. We don't get every piece of information. Why do it? Well, it's going to be quicker than trying to gather every piece of information. It's certainly going to be cheaper. I mean, you've got to usually pay someone to go and survey people and things like that. Accuracy. Once you start dealing with large numbers of data, there's more chance of mistakes happening. It tends to be more accurate if you sample rather than try and get every piece of data. And necessity. If you're doing quality testing, sometimes it's not practical to test every item. Certainly if you're going to destroy it. So an example would be like matches. Now imagine that. Okay, I want to see if this batch of matches is good. Oh no, we'll just light every one of them. Oh yeah, that one worked, that one worked, that one worked. It's not practical. So how should you draw a sample? Always randomly. Okay? They should always be random samples. And that basically means that any piece of data that we want to collect has an equal chance of being selected. There's no bias in the selection. Now, what that means then is that if you've got a true random sample, it might not actually be a great representation of the population. Just imagine randomly, well, let's say we were surveying the population of Australia and we just want to randomly select 1,000 people, but we happen to pick, what shall we say, 1,000 people, and they all came from New South Wales. Now, there are some things that happen in New South Wales that are different to Western Australia and so on. So it wouldn't be a good cross-section of the population. But that's what happens with random. I mean, you could get anything. We have different terms and notation depending on whether we're taking the whole population or just getting a sample. So when we go and collect data, if it's just a sample, we call it a survey. We're going to survey this group. Whereas if you're gathering every piece of information, we call it a census. I guess the most common census that you would have heard of is what the Australian Bureau of Statistics does every 4 years, 5 years, where there's this huge form that every household has to fill out, how many people are living there, what are their ages, and all that sort of stuff. But they want to gather every piece of information when they do that. Notation for probability. Well, in fact, it's only really true to call it probability when we're talking about the entire population. When it's just a sample, it's actually called relative frequency. We have different notations, so probability of X, whereas relative frequency we tend to write F with a little r. When it comes to expected value, for the population we use mu, the Greek letter, whereas in the sample we have X with a bar over the top. We tend to use the Greek letters for population, but the Latin letters or the Roman letters for sample. Variance, then we have sigma squared for population, again the Greek letter, whereas in the sample we tend to use S squared. Now, as n approaches infinity, so the size of our sample gets bigger and bigger and bigger, basically the answers should get the same. So the average of the sample should approach the average of the population, and similar with the deviations. So we're going to roll 2 dice. We're going to use the theoretical probability distribution. So the theoretical one for this would be the entire population. What would happen in theory to calculate the expected value and the variance for the population. So here we go. Here's my distribution table. Again, the theoretical probability. The probability of rolling a 2, for instance, would be 1 in 36. There's our decimal for that, and so on. And I've already worked out the xpx and the x squared px to make life easier for ourselves. The expected value would be 7. Also explains, by the way, when you have dice, why the opposite sides of a standard dice add up to 7. That's why they're designed that way, because when you roll 2 of them, the expected value would be 7. The variance turns out to be 5.83 repeater. Okay, So they're our theoretical ones. Oh, that, by the way, means our deviation. We find the square root of that is 2.4152. Okay. If I was to plot them, and it's theoretical, you get this lovely symmetric shape, and there would be our graph. Well, now we're going to do an experiment. Well, sort of. Here's one I did earlier, where we roll a dice 50 times, then 100 times, then 500 times, then 1,000 times, and compare those samples with the actual theoretical data. Now, of course, I didn't actually roll them. I created a spreadsheet to do it for me. But when I did it 50 times, this is what happens. Up above, there's our theoretical ones, and below, this is what happened. Actually, they're not the same, and it would be surprising if they did turn out to be the same, unless I got incredibly lucky. The expected value of my little experiment there, my sample, was 6.42, not 7. That was off by about 0.58. The variance turned out to be 5.8036. There's a slight difference there in the deviation, very close, but 0.0061 for that one. If I was to plot my experiment or my sample on top of the other one, you can see how closely it fits the theoretical data. Not that great. I only did 50, I suppose. Okay, what happened when I did it 100 times? What happened? 7.16. So that's off by 0.16. The spread, that actually was a little bit further out than the last one, 0.0250. There's the graph. You say, okay, it's coming a little bit closer. But theoretically, what should be happening is, as these numbers are increasing, we get closer and closer to the theoretical probabilities. Okay, 500. That's what happened with 500. 6.86. Off by 0.14. And there's my deviation. Match that graph. Okay, it's coming in a little bit more. 1,000 times. 7.042. Not too bad. And so on. And our graph, it's starting to get really close. I say, I could do that 1,000 times again, and it would look nothing like it maybe, because it's totally random. These numbers are getting pulled out. But this, when I did it, what they turned out to be. So that's a little bit about experiments, sampling, and so on. 13D, I've just picked 4 out there for you to have a bit of a play with.